Okay, so we are going to study more about computation with basis. So essentially, bases in a vector space give us a method of computation. So writing it computation. In some sense, they establish coordinates of a given vector in the vector space. So, for example, let's say we have a given basis of a vector space V. Now, by definition, any vector can be uniquely expressed as v1 x1 plus v2 x2 vn xn, where xi's come from a field. So they can be expressed in exactly one way. The scalars x of I are called the coordinates. So I'll just represent them by a column vector. So if I have for example, take an example of a vector space of column vectors. From a field Fn. So this is a space of n-dimensional column vectors. So I have a basis which is an ordered pair. Let this be a basis. So therefore B is a n by n matrix. So I can write B as all these columns stacked together. So as an example given in the book, V1, V2, Well, then B is 1, 3, 2, 5. This is the matrix of the basis vectors. Uh, we usually deal with what is known as the standard basis, which I denote by E2 En is the standard basis. And by standard basis, I mean this matrix E is essentially an identity matrix. That's called as the standard basis, where I have, the basis vectors are essentially 1, 0, 0, 0, 0, 1, 0, 0, so on and so forth. So I can denote dx as v1, v2, vn, and the column vector x1, xn, and that gives me the vector. So this helps us find the coordinate of some vector. So for example, let y be the coordinates. So let this be the vector. So how do I find the coordinates of the vector? Well, by definition, this vector has coordinates xn. So this was b, x, this was equals to y. So therefore b inverse y is equals to x, the column vector of the coordinates. So that way I can find the coordinates of any vector y. So as a concrete example, let's say the previous example I had the matrix B as 1, 3, 2, 5. If you calculate the inverse, that turns out to be -5, 2, 3, -1. I'm not doing this in my head. It's already, this example has been given in the book, so you can verify it. So let I have a vector 1, 4. Its coordinates with respect to the basis B are nothing but, if you evaluate it, -2. So the vector y in terms of my basis vectors, so basis vectors were again 1, 2 and 3, 5. In terms of these basis vectors, the coordinate y is 7v1 minus 2v2. Of course, B has to be invertible. So we can write down as a proposition, and that is, let A be an n cross n matrix with entries in a field F. The columns of A form a basis of Fn if and only if A is invertible. So, well, it's easy to show that. I mean, if A is invertible, we know Ax equals to 0 has only a trivial solution. Remember, we did this last time. So, this implies that the matrix A consists of vectors which are linearly independent, and also the fact that A is an n by n object. So I have A is v1, v2, vn. I have n elements for A, and I need n elements for vector space V equals to Fn. So I have n linearly independent solutions, n linearly independent vectors, which is going to give me an invertible matrix. So I can prove it both ways. So again, I repeat the proposition, which is to say that columns of A form a basis if and only if A is an invertible matrix. Because only if the matrix A is invertible, I can show that the columns of A form a linearly independent set, and that is one of the conditions for it to be a basis, that I need linear independence and something to span the basis, so to speak, span the vector space. And I can also prove it the other way around, that if A is invertible, then the columns of A form a basis. Okay, so far we have been dealing with vector space of column vectors Fn. It is possible to define all we have seen in an abstract form of general vector spaces. So let's go to an abstract form, and we'll see that all we have learned just translates into it, abstract form of general vector spaces. So here we consider ordered set of vectors. Now notice they are not column vectors necessarily. They are just ordered set of some vectors v1, v2, vn. So now this is not a matrix, but I can still define some. This is not a matrix product, but I can define a scalar product. So that gives me v1 x1